Hello, statistics students. In our last chapter on confidence intervals, we started with a confidence interval for a mean when we knew sigma, and then we went to a mean where we didn't know sigma. We're going to do the same in this chapter on hypothesis testing. That could be interesting. Let's see what I was showing there in a moment. So we have a confidence interval for mu. We knew sigma. Here was the formula we used. Notice the z and the sigma team up. And when we were doing a hypothesis test, we calculated our z statistic, which was this. Then in the last chapter, when we did a confidence interval for mu when sigma was not known, this was our formula for the confidence interval. Notice that T and S are teaming up. And now we're going to do a hypothesis test for a mean when we don't know sigma. All we know is S, a sample standard dev. This is going to be our t-statistic. And notice how very similar it is to a z-statistic, except we're dividing by S over root n instead of sigma over root n. So let's dive right into a practice problem. A lot to write here. We'll discuss it more in class. I'm just going to walk you through it. Listen first, then you can pause the video and copy this down. Here are my hypotheses. I claim that mu, whatever we're measuring mu, is less than 1200. That's what I want to prove. So my null hypothesis is the complement of that. I take a sample size of 7 for whatever reason. The population is approximately normally distributed. I got an X bar of 1125. Now you say, well, that's less than 1200, prove. Well, no, because even if mu was exactly equal to 1200, which is what we're going to put on our diagram, because remember the definition of a p-value. It's the probability of getting the results we got or something more extreme, assuming the null hypothesis is true. So even if mu is 1200, how likely is it that we'd get a sample like this? If it's pretty likely, this isn't strong enough evidence. If it's not very likely, it is strong evidence. All right, so our sample of 7 had a mean of 1125 and a standard dev of 55. Again, I want to point out, this is a sample standard dev because it's the standard dev of these 7 samples here. In this case, for whatever reason, alpha is 10%. We have a sample size of 7, so our degrees of freedom is 6. Let's draw a curve. We're going to center it. It's a T curve because we don't know sigma. So it's pretty much the same shape as the normal, just not going to be as tall, and the tails are going to be fatter. So centered at 1200. The standard dev, or the standard error, which is the standard dev of this sampling distribution, is S over root n. So I go 1200 plus 20. Okay, I didn't need that. I need 1200 minus 20.79. And I got 1125, which is, way out here somewhere. Oh, there it is. And it turns out that t-statistic, that 1125 is 3.61 standard devs below the mean, so it's way out here. So if I go the p-value method, if you look up in your book, don't have my book right here, you'll find, and remind me to go over this in class, you'll find that the p-value is somewhere between 0.5% and 1%. That's all you need to know because alpha is 10. P is less than alpha. P is low, reject the hoe. If you do the critical value method, if we have a one-tailed test and alpha of 10%, then all 10% needs to be down here. You can look on your table with 6 degrees of freedom and a one-tailed alpha of 10%, and it'll tell you that your t-statistic is going to be 1.440. However, look at the picture, that's for the upper tail, which means this needs to be negative 1.440. So this green area out here is my rejection region. My t-statistic is in the rejection region. So in both cases, we're going to reject the null. And if you do this right, both cases will always match. That's kind of the idea. So let's write our 3-part conclusion statement. Part 1, we reject the null. Part 2, at the 10% level. Part 3 is to state your conclusion in English. Conclude that the average cost to insure a sedan, that's what mu was, is less than $1,200. So let's talk inferences about a mean. Here we go. Again, if you don't know sigma, we're going to use T. Again, this is about population means. If you don't know sigma, we're going to use T. If you know sigma, we're going to use Z. Okay, what was that? Yep, all right. Moving on. So why does this work? How does this hypothesis testing business work? Well, it all goes back to the central limit theorem. Given a population with a mean of mu and a standard dev of sigma, if n is big enough, then the sampling distribution will be approximately normal with a mean of mu and a standard dev of sigma over root n. So what we're doing is we're saying where on the sampling distribution is my particular sample. Recall that a sampling distribution is if you could take every possible sample of size n from your population, average it and plot that average, you would get the sampling distribution. So now what we do is we say, so here's our population. Nope, here's our Z population with sigma over root n being our standard dev of our sampling distribution. Here's our T curve, shorter and fatter tails here, where S over root n is the standard dev. So anyway, we take our all possible samples of size n and we graph them. Then we say, this one sample that I just took, where is it on the curve? So since we're talking T's, let's use this one. Here it is. Now, what's the probability of getting this result or something more extreme, assuming the curve is centered here at mu 0? And I should change that to mu 0. Nah, I'm not going to change it. So let's do another problem. Again, let me walk you through it, then you can go back and copy down what you need. So Jeffrey says, on average, the local police arrest more than 50 people a day. You think Jeffrey's a wackadoo. Test his claim. Now his claim is that mu is less than 50. Okay, no equal sign there, so that's going to be alternate hypothesis. Here's our null. We're going to go alpha is 5%. So now that we've established our hypotheses, then we gather data. We gather data for 2 months, which is 61 days. And we got an average of 51 people a day with a standard dev of 6. Well, you might say, hey, 51's Oh, wait a minute. I wrote this wrong. You think Jeffrey is a wackadoo. You're trying to prove Jeffrey wrong. That's why mu is less than 50, because you're trying to prove him wrong. And this is his statement. Okay, so his statement is more than 50 per day. Sorry, early in the morning as I make this video. So this is what you're trying to prove. What you're trying to prove is almost always what you make the null hypothesis or the alternate hypothesis. I know FRL says wherever the equal sign is, make that your null. I don't agree with that. So mainly because how somebody words something isn't necessarily how it's going to work statistically. You got to go, what are you trying to prove? And you're trying to prove he's a wackadoo. So you might say X bar here is greater than 50. So you don't have any evidence at all to support this. So he must be right. Let's see what happens. So I calculate my test statistic, and I get a test statistic of 1.3 standard deves. My sampling distribution standard dev, also known as the standard error, is S over root N. So mean is 50 because that's where the equal sign was. Mu is less than, or mu is greater. Gee whiz, need to get more sleep. Mu is greater than or equal to 50. So 50 was where the equal sign is. So this would be 50.77, and here's 51. I have 60 degrees of freedom. And if you look, now here's a catch. Why didn't I shade this area out to the right? Can you answer that to yourself? Because the alternate hypothesis says mu is less than 50. So we're shading to the left. Alrighty, so you should be able to tell looking in your table. Do this on your own before we go to class. Make sure you can do this. Your p-value is going to be between 90 and 95%. That is not low. We're going to fail to reject the null hypothesis at the 5% level. And so there is not enough evidence to say that the average is less than 50. But Jeffrey was saying that they arrest more than 50 people a day. So the way I say, so what are you really concluding? We're going to say, we didn't prove the null hypothesis. We just didn't find enough evidence to go with the alternative. So what I would say here is, what we can conclude is, conclude that the average number per day is at least 50, which is the null. We can conclude that. We didn't prove it, but we can conclude it pending further evidence. In other words, we're trying to gather evidence for the alternative. We didn't gather enough evidence for the alternative, so we're going to stick with the null for now until we get more evidence. So in this case, Jeffrey might be right, but he's still a wackadoo. Now, something I'd like to point out is Jeffrey said the local police arrest more than 50 people a day. According to our textbook, then they would say put mu as greater than 50 and test his claim. I say, what are you trying to prove? You're trying to prove he's a wackadoo, so you want to prove he's wrong. So you have to move the equal sign up here. What's the probability that the police arrest exactly 50 people per day on average? Don't worry about that equal sign. You can move it up to here, it's okay. But it must be in the null. Alrighty, we do have a quiz coming up. So let's take a look at a couple of example problems from the quiz. You know what? We don't need to quiz that on the video. We'll go over that in class. So understand that what I want you to get out of today's lesson is that we've started doing hypothesis tests. We initially did hypothesis tests for means when we assumed that we knew the population sigma. And in this lesson, we did a hypothesis test for mean where we admit we didn't know sigma. All we knew is the sample standard dev S. The t-statistic looks very much like a z-statistic, except that it is S over root n in the denominator instead of sigma over root n. So hopefully this is making sense to you. You've had plenty of time to go back, copy down what you need to, be ready to go in class. Have a great day.